The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
All right, so now I'm going to walk you through some examples, and just so you know where this stuff is. So you all have your EloGrid accounts, and in your EloGrid accounts, and I'm looking over here because these people are going to check to make sure I don't say anything wrong. So this is, by the way, this is Chansa Byun over here and Julie Mullen. They are our expert consultants, PhDs in computational science that help you all, and we are all eternally grateful to them for helping us get all this technology to work. If you go to your EloGrid account, there should be a link in there called Tools. This is where all the software is that we provide as part of EloGrid exists, and there'll be one called D4M API in there. So there'll be a folder just like this, okay? And just so you know, so all the lectures are there for you, and I am putting them all in for public release. And all the software we're going to post on the internet too, and so just make it easy for you to use with your government, use with your sponsors, use in your projects, all that kind of stuff. We try and do that so that people aren't constantly asking us, well, what can I share? It's like, we're going to put it on the internet. So there you go. We want to focus on the examples directory here. The order of the examples is numerical order. So we're going to go through examples in the folder called 1, and then 2, and then 3. This really corresponds to kind of the first 3 lectures, then the next 3 lectures, then the next 3 lectures. Okay? And so today, we're going to go in here to this first one, and then here, it's kind of like the first 3 of those 3. We're going to go and we're going to review this set here. Okay? So these are the examples. All have this sort of, they basically take the first 2 letters of the folder, in this case, Assoc Intro, AI, 1, 2, 3, 4. Those are the actual examples. If you see other files in there, those are supporting files. You don't run those directly. So I'm not going to start my I always run MATLAB from the shell. Other people run from the IDE. I'm going to create a shell here. Okay. So in the folder, I'm going to start my MATLAB up. This will take a minute because we're using 2012B, which is a little bit slower on this computer. All right, there we go. And you'll be pleased to know I develop all the D4M software on this little computer. And people will wonder, well, why don't you get a big giant workstation to develop your programs on? It's like, well, because if it feels okay for me on this computer, I know that most of you have much better computers, and it should feel very, very, very good for you. All right, so we're in the folder, and I'm just going to run the first program, II1 setup.test. Actually, before we even get into that, the first thing you want to do is check, before you run this, that your D4M code has been properly set up. The simplest way to do that is when you start MATLAB, if you type help D4M, and you get a list of all the functions in D4M, then that means that your path is set up properly. And this is just a list of all the different functions. We break them down in different types, and a little sort of like how to set up here, although a lot of this stuff is written for more people on the outside world. Then we go through all the functions, and we categorize the functions. Some are functions that we really expect you to use all the time. Some are functions that you might use, once in kind of rare instances. And then we also have functions like, look, they're there, they're in the library. These are really not meant for you to use, though. They're really internal supporting functions, but they're there in the library. All right, so that's the first thing you want to check, is to make sure that's set up. If you have any issues, send email to grid-help@ll.mit.edu, and the people will help you and check it out. And Don't be surprised if some of you do have an issue. This is the first time we've really rolled it out to such a large audience, and so we absolutely expect people to have little things that will pop up. All right, so I'm going to run the first example here. I should say we also have tested all of this stuff for those of you who are utterly averse to commercial software, depending on your religious preferences. We also run with GNU Octave, which is the GPL version for those of you who refuse to run non-free software. And so, so all the stuff should also work with that as well, just for those people who prefer to use that type of environment. But generally, MATLAB, is pretty available here, and so we certainly encourage you to use that. So we're going to run the first test here. AI1 setup.test. There we go. Yay, it worked. It's embarrassing when you're recording and these don't work. So I'm going to walk you through some really rudimentary stuff here in this example. So one of the things in D4M that you're dealing with a lot is lists of strings. Long lists of strings. Millions of distinct strings. Now, MATLAB has data structures that do support lists of strings. Cell arrays being one of them. There's other data structures that you can use to do that. They naturally support these, but they tend to be very memory intensive and very slow. And so given our whole thing here is we have a real focus on performance, me giving you a great tool that's 1,000 times slower than other techniques is not very helpful. So we are going to be dealing with lists of strings all the time. And so in D4M, a list of strings is a row vector of characters. Okay, I've highlighted here. And the last character in the row vector is the delimiter. In this case, it's the comma here at the end. That is the delimiter. It can be whatever you want it to be. It can be a semicolon, it can be a dash, it can be a space. I tend to recommend new line, which is ASCII character 10, very safe delimiter. But whatever that last character is, that's the delimiter. And you can have different lists, different strings with different delimiters. It should handle those situations just fine. But within a list of strings, it needs to be that last character will be the delimiter. So I'm actually creating here a list. I'm going to be creating a set of triples here: R, which is the rows; C, which is the columns; V, which is the values. And so I have an R, which is this. I have a set of C here, which is this vector here, and then a list of values. And the values in this case are just appending the row and the column together with the dash. And all three of these use the comma as it's the last character, as the delimiter. All right. And now I'm going to create an associative array, which is the fundamental data structure in D4M. It's what allows us to bridge linear algebra and strings together. So this is the constructor command for an associative array. It's assoc, and then we give it a list of row keys. These are called, we often call them keys. List of column keys, a list of string values, and this constructs the associative array A. And in MATLAB, since I haven't terminated this with a semicolon, it now will print out the list of triples. So now you can see the list of triples we can construct here was row A, column A, value A dash A, row AA, column A, value AA dash A, and I won't read the whole list. Yes, Daryl.
Question. It seems like your delimiter is included in the end of your
That is an artifact of this printing out display. It will show you the delimiter that you actually used here. And it's good to know that you.
It's not really there.
It's not really there. Well, yeah, I mean it's there and it's not there, but it's showing you the delimiter. And after a while, you just kind of learn to ignore that. The only time this does become a little bit of an issue is if that is the new line character, then the formatting gets a little bit. And we've actually built-in routines that allow you to just take an associative array, replace the delimiter with something nicer, in one command, so that you can print it out and it doesn't look so crazy if you're using a new line. Typically, though, you tend to be doing this printout command on small things. So it's fine. So that's the whole list you see there of all the different entries. If you use the disp command, it will actually display the internal structure of the associative array. And an associative array object in D4M has 4 fields total. That's it. We do everything with just 4 fields. And the 4 fields are a set of row keys. This is a lexicographically sorted list of the unique row keys. And it's stored as a string list. So in this case, we had 6 unique row keys, and we have 6 entries in this row string list. Likewise, the column is the same thing. We have these 6 unique entries, and you see they inherit the delimiter that was passed into them. If I'd used different ones, you would see different delimiters. And then the value, which is another list that shows all the different strings, okay? And then a matrix, which shows, which is a 6 by 6 matrix. So this is a 6 by 6 associative array, and this is the pointer. Basically, the value stored in this 6 by 6 sparse matrix points to the index of the value. So you can view that as a pointer to the values, and this is how we can have values that are actually strings. That may not be quite clear, but there's an easier way to do this. So we have a little function here called display full, which produces a nice tabular view of the data. So here's the row keys, the column keys, and the values, and you see this was the matrix I constructed, had a full first column and a full first row, and then values along the diagonal. And then what we're going to do is we want to save this, we want to write it out, so we're going to write it out we have a function here to CSV, so I pass an associative array, I give it the row terminator and the column separator and a file name, and we'll write that data out to a CSV file, which is very convenient. If I actually hide that, you can see here is the CSV file. And so you can look at it. There's the CSV file. So we can zoom in on that for you. And you see, there we go. Those are our 6 rows, 6 columns, our dense first row, our dense first column, and our diagonal. Okay. All right. So let's go back here. Now let's go on to the next example, which is going to be AI2. And now we're going to talk about how we've sort of described how we put data into an associative array. We're now going to talk about how we query it or get data out of the associative array. And one of the things that's very nice about the queries that I will show you as we get to the later parts of the course, we do databases, whether you're querying an associative array that's in memory or a binding to a table, it's the same. We try and make it so that almost everything you would do on an associative array, you could also do on a table. So you can write your programs on associative arrays and then switch a couple things, and now it should also work on tables in a database the same way. And so we try and preserve that concept. The only difference is that a table in a database just can be much, much bigger than a table than in an associative array you would have in your memory space. All right, so we're going to run that. That's the next example. So the first thing we did is, well, we wrote out the associative array. We're going to read it back in. So we have a nice function here called read CSV that reads CSV files. Just so you know, Microsoft Excel does write out a non-standard CSV file. In Microsoft Excel, most of the common, that is, if you have a row that is empty after a certain point, it won't write out those commas, which is technically probably not conformant with the official CSV format, although I don't know there is a officially written down CSV format, right? You can describe it in one line. So you just have to be careful about that. When we see this issue, people write out a CSV from Excel, and if there's an empty if the last row is not fully dense, or last column is not a dense column, you can get this issue and it will screw all this stuff up. We also don't support quoted strings. The way to do that, though, is to create a TSV file. So put tabs in there, and we support tab. If you just call this a TSV file, when you write it out, you could have your separator be a tab instead of a column, a comma, and then you're all good. And so that's how we support that. So we're going to so that's how we read it in. And now we're going to do a whole bunch of different queries. These are all what are relatively complicated queries. So the first one here is get me rows A and B. So if I pass in a string list, just like the, oops, didn't want to do that. Let's see here. If we pass in a string list of the same type that I had before, and I just say this exact same type of indexing that we normally have in MATLAB, where you're like, I want to get a set of rows, I give it a set of rows. And so this says, get me rows A and B, and get me the whole row, colon, use the standard MATLAB syntax that colon means whole row. Likewise, if A was a binding to a table, it would deliver the exact same query to the database and return the exact same thing in associative array. Here's another more complicated query that says, get me all rows containing A. So our wildcard character is a little liberal here. It will just give you anything containing an A. It doesn't really respect beginnings or endings or anything like that. It's kind of a regular expression. And then and this says get any row containing A and columns 1 through 3. So we can use numerical indexes. Sometimes you just like, I don't care what the row keys are, just give me the first 10 columns or the first 10 rows, and that will return this. Okay? This is one feature that does not work on all databases. Some databases have a concept of a numerical index of a column, and some databases do not. So it's dependent on the actual database. Here's another one. This is a range query. So if you remember in MATLAB, if you do colon and 2 values, it gives you a range. So we can do a range query here. So A, give me all columns A through B. If you really wanted to just we have something called a starts with, which is something like a lot of times people are like, I want to just get the rows or the columns that begin with a certain string. So we have a little shorthand routine here that constructs that for you. So this says, get me all rows starting with A and C. Likewise, I can do the same thing with columns. I can say, get me columns A and B. I can say, get me all columns that contain A with columns with rows 1 through 3. Like I said, I can do column ranges here. I can say, get me all columns A to B. Likewise, I can do the starts with command as well. It says, get me all columns starting with A or C. And then finally, I think this is kind of fun, we can actually query the values. Again, this is a feature that's not supported with the database, but is supported with the associative array, which is if I say, return an associative array where all the values are greater than B. I'm sorry, less than B. Okay? So let me just show you what that one looks like. So this was that query, and this is what it looks like. So I do display a V, and you see now we don't have any values that begin with a B. All the values. Okay? Another thing that we should notice here is that this is now a 3x3 matrix, not a 6x6 matrix. Associative arrays never store an empty row or an empty column. That is a big difference between traditional sparse linear algebra and associative arrays. In sparse linear algebra, you can have a row of all zero, an empty row or an empty column. Not in associative arrays. Associative arrays, you either have, there's going to be, if you have a row or a column, it's going to have an entry unit. Yes? So basically, all it does, so it's basically, so if we had a value that began with C, that would also not be included. So it's basically, lexicographically, we compare the value AA with B, and we say, is it lexicographically before B? If so, it satisfies the condition.
Jeremy, is that equivalent to saying if I were to put all these values into a dictionary, would it appear before B?
Yes, yes. So that's the policy that we made. So strictly, the algebra of associative arrays doesn't require lexicographical ordering. That's an implementation fact. It's a very important implementation fact. We are constantly maintaining lexicographical order inside the data structure. Yeah, Daryl?
I may have misheard. It returns a 3 by 6.
Oh, that's right. Yeah, 3 by 6. Sorry, 3 by 6. Yes, yes, because these are full here, right? But you see that the ones, you know, none of the ones with B in it happen to be because they didn't satisfy the criteria, so therefore they're empty, and so therefore. So it's just a very important thing to know. All right, moving on here to the next. You define other orderings. The mathematics would no doubt admit that. It's really baked in, though, into the implementation. I mean, because we rely on the MATLAB sort command, and as far as I know, that does not allow you to have other orderings. Now, you could obviously do rehash. You could hash your rows and keys to some other thing, and then have an associative array that maps those back and forth. In fact, people do that all the time, and just have, you know, and you could do that. But that's how you, if you really, really want the ordering. The main thing, though, is to kind of think of it, though, is that the ordering doesn't really matter. It's really a device that allows me to do fast lookups. And, you know, you shouldn't really care about the ordering. All right, so let's move on to the next example. So actually, so we're going to do AI 3. So now we're going to do some math on this stuff, okay? So here we go. All right, so once again, I read in my, my data that I constructed in the first example. The values of that data were strings. But if I want to do math, sometimes I don't want to do math on strings. Sometimes I want to do math on numbers. So in D4M, the associative arrays can also be numbers, which can be very convenient for doing mathematical operations. And so what we have here is we have this command called double logi, which is just shorthand for, and it's kind of cut off here, applying logical to the associative array, which takes all the values and converts them just to a 0 or 1, basically throws away the strings, or if it was a numeric value, just means, are you there? You're a 1. If you're not there, you're a 0 or you're empty. And then since we can't do arithmetic on logicals in MATLAB, we have to bump them back into doubles. So we do this so often, we've actually made a little shorthand here where we call double logi, and you'll see that all the time in the class because I just don't like to type all the characters of writing double logical. It gets very redundant. And now if we go and look at that data again, we see when you do display full that instead of where before we had values of these various strings, we just now have numbers, just ones. So that's convenient. Now I can do arithmetic on them. So let me do the first thing here. One of the things I might want to do is sum all the rows. So the MATLAB sum command, it's basically you're giving it essentially the dimension to eliminate. The first dimension we want to eliminate or sum over is the row dimension, so that means it's summing up all these rows. It's basically squishing the matrix and summing them up. And now we have a new associative array, which is essentially a 1 by 6 associative array. You see now that the row key is empty because when we sum, the definitions of the rows sort of kind of go away. So you don't have to have strings to be your row keys. You can have numeric row keys, just leave the row entry empty, but there are some cautions with that as well. So when we sum that, and you see down we have all the columns, the values, because they're not strings, are just stored in this A matrix itself, and you see that we had 6 and 2 and 2 and 2 and 2 and 2. So when we sum these up, that's exactly what you would expect. Moving along, we can do the columns. So here I'm going to sum, and then I'm going to do display full, which is the same as just kind of listing it. And we see here we now sum the compressed all the columns. So we have a column vector, and this shows the row labels of that column vector. We now have a new column label, which is just 1, and then you see the actual values there. Again, a very useful thing. People who do this all the time, summing of their rows and columns. Let's do a simple join. So I'm going to say, give me a column vector A, get me another column vector B. All right, and I'm going to join these two together. Now I could just do AA and AB, but I'd get an empty matrix. The reason is because it would attempt to do the joins and they would have different column labels. And so when we do joins, we're intersecting the two sets of row and column keys together. And if they have those are just separate columns. They AND them together, they have no intersection. However, if we have this function called noCall, which essentially blows away the columns and basically gives them all, in this case, a column value of 1, we can now AND them together, and we can actually find where these two things have a common value. So that's a fairly simple way to do a join. This is something called a facet search, which basically says, all right, I'm going to join these things together. So I'm going to create a column vector, but then I'm going to transpose that over here. So I transpose it, and then I'm going to multiply it back with the original matrix. And this gives me a count, essentially, of all, given all columns or all rows that had an entry in column A and B, can you now sum up their rows? And this is this is actually the mathematical basis of, if you ever do in Google search and does auto find, it's essentially trying to do this type of operation. It's trying to guess what the next most popular topic would be. And this essentially, this mathematical operation does that kind of thing. We actually have a bunch of applications in the lab that use this quite heavily. And I can display the transpose of that, so to make it a column vector. And as you see here, we have a bunch of columns here and then values. And then we can actually now do things like sum and normalize, so we can divide. So I'm going to normalize them. You can display that. You see now you get the probabilities associated with these things. Basically you can just kind of go on your way doing math. This shows essentially the correlation of the columns A and B, but why not just do all the correlations at once? So if I'll focus on here, so we have this function square in, which is the same as A transpose A, but a little bit faster if you're just squaring something with itself. I'm going to get the diagonal of that. So if I use this function ADJ, which stands for adjacency, it will just pop out that A matrix by itself. Whenever you use ADJ, you're getting a straight, sparse MATLAB matrix, and you can do any operation on that you want that MATLAB supports. So we highly recommend that. If you can't figure out how to do with the associative arrays, just pop out that adjacency matrix, do whatever you want, and then you can just, as long as you didn't change the size, you can just stuff it right back in at essentially no cost. So this just basically copies that field out, and we're going to get the diagonal. The reason we want to get the diagonal is when we do correlations, we always get this dense diagonal. I want to eliminate that. So I'm going to then now take the adjacency matrix of the original correlation matrix, subtract the diagonal, and then we have this function put ADJ, which is kind of the inverse of ADJ, which just says, I have an associative array, replace that A with this. No checking, instantaneous copy, very fast, but make sure it's the right size. If it's the wrong size, or you reoriented the columns in some way or the rows in some way, then it won't make any sense. So it's a little bit of an advanced feature, but it's a very powerful one. You can pop stuff in and out of these structures very quickly, and that way, if you ever need to do math that we don't support, you can just do that directly. And so if we look at that, we see what you would expect, a nice correlation matrix here, symmetric, with no diagonal and the counts of each one. All right, here. So let me move on to the next example here, which is AI4. And this just shows you different ways to construct associative arrays, some of the various kind of more degenerate cases. So I have a bench, I'm just creating a string here and a bunch of numeric values. The point here is when you construct an associative array, one, we have full support for all these degenerate empty conditions. If you give me anything with any kind of empty, we're going to return an empty associative array. MATLAB has outstanding support for empty objects. You can just keep on passing. You don't have to. We basically, what I'm saying is we do a lot of checking if the thing is empty, short circuit, return an empty type of thing, so that you're not having to constantly check if something is empty or not in order to proceed. So that's what we do there. That's just showing that all these supported. In addition, you can do mixed types. So when you construct an associative array, if one of the values is a scalar, like for instance, you can have that. You don't, normally as in the MATLAB sparse constructor, when you give it a set of triples, they all have to be the same length, or any of them can be scalars. So this just says I have a bunch of column strings, a bunch of numeric values. Oh, and by the way, they all have the same row. So this is a very quick way to construct a row vector. I don't have to go and replicate this A that many times to make this work. Likewise, here I could have a numeric value for the actual rows, a string value for the columns, and I want everyone to have the same value. They're all going to have a value of A. And you can do variations on that theme. So these are fast ways to create row columns, row vectors, or column vectors, or values with all a constant numeric value and other types of things like that. And then we can just display one of these, and you see here, I think it was which one we displayed, this first one, which is a row, and you can see when you display that, it just has one value for the row. These are the different columns. These are the different values. And again, if we display full, you see in the tabular form, that's what you have. So that brings us to the end of the first lecture. I'm happy to stay for questions that people might have. Please go and check out your Yellow Grid account. Copy the examples. Don't try and work out of you'll get like permission denied errors and stuff like that. Copy the examples to your home directory. Try and get your D4M working. Try and run just this first example. Make sure it behaved the same way that we had here. And then send email to grid-help. And then as we get into the next week, we'll do homeworks that are a little bit more substantive. But this is just to make sure the technology is working for you. And we'll wrap it up there. Thank you.